Hey guys, so I'm going to quickly go through some of these properties of binary trees and prove them via induction. So bear with the camera here, I'm kind of trying to make do with my cell phone. The first property is that the number of nodes of a perfect binary tree of height h is going to equal 2 raised to the power of h plus 1 minus 1. So this is actually the same as saying find the max possible nodes in a binary tree of height h. And the reason being is because if you think about it, the max number of nodes in a binary tree is actually a perfect binary tree, because a perfect binary tree stipulates that all of each node has 2 children, with the exception of obviously the very last bottom level. So first step in this induction proof is going to be to show a base case. So we're going to say that the base case is going to equal, let's say, 0. So we have h equals 0. That's going to be a tree with just a root node. Bear with my pen here. And we can plug the formula in for 0. So we're going to say that 2h, number of nodes, should equal 2 to our h, which is 0 in this case, minus 1, plus 1, sorry, minus 1. 2 raised to the power of 0 plus 1 is going to give you 2 to the power of 1, which is 2 minus 1, which all comes to 1. As you can say by our illustration here, we do have one node in this tree, so that's correct. Just for visualization's sake, I'm going to do one more. Let's say base case equals 1. So if our height is 1, that means our tree looks like this. So we're going to say 2 to the 1 plus 1 minus 1 equals 2 raised to the 1 plus 1 power is 2 squared, which is 4, minus 1 is going to give us 3, which does indeed match the number of nodes in our illustration of our tree here. So now we know it works. So we're going to assume that 2 to h plus 1 minus 1 nodes holds true for k. So we're going to write that as, assume that for tree of h equals k, number nodes equals 2 to the k plus 1 minus 1. We're going to use this definition in our proof. So imagine now, what we want to do is we want to prove it for the number that comes after k. So if for height k, this is the formula, we now want to prove that for height equals k plus 1, number nodes equals 2 to the k plus 1 plus 1, all minus 1 is going to give us the value of our nodes. And this right here will simplify to 2 raised to the power of k plus 2. I just wrote out the long way, so if your algebra skills are a little rusty, you can see how that works out. So I'll just write that out for you. 2 to the k plus 2 minus 1. Okay. So how are we going to prove that? This is the hard part here. It's not so hard though, because if we've shown that a tree, let's say a subtree of A, get a different pen. If we've shown that a subtree of A here, let's say this has a whole height of k. All right, we're just gonna dictate that this height is k. Because that we're saying this height, the height of this tree is k, we know by our definition that we have up here, and we're assuming that it's true for k. Assume that formula gives us the number of nodes in k, then that means that the number of nodes in this tree here is equal to that formula. So we have 2k plus 1 minus 1 equals number of nodes. If we wanted to get a tree of height k plus 1, what that means is we would have one more level of nodes underneath A. Everyone see how that works? So, because it's a perfect binary tree, if we were going to add one more level to this tree, which would increase the height by 1, we'd have to have nodes coming off of the end of each of the current leaf nodes in A. So we can draw that by doing this. We could say, well, what if we have a root up here, and extending from the left of the root, we had a copy of A, and coming out of the right of the root, we have another copy of A. Now A, we said over here, has 2 to k plus 1 minus 1 nodes. So all this is 2 to the k plus 1 minus 1 plus another 2 to the k plus 1 minus 1 plus our one new root. So now we just want to show what we're trying to prove up here. See, the point is we're trying to prove that for h equals k plus 1, the number of nodes equals 2 to the k plus 2 minus 1. So now we just have to show that our equation we're generating here is equal to that. So we're going to do that here. We're going to say 2 to the k plus 2 minus 1 is equal to 2 to the k plus 1 minus 1 plus, and that's our first A, 2 to the k plus 1 minus 1, that's our second A, plus 1. So now we just have to simplify the right side to try to get it equal to the left side, right? So we're going to say that these cancel out. So we're going to be left with 2 k plus 2 minus 1 equals all right, now when you have 2 to the k plus 1 plus 2 to the k plus 1, when you add a power of 2, when a number is a base of 2 and it has the same power, you just increase that power by 1. So 2 to the k plus 1 plus 2 to the k plus 1 is equal to 2 to the k plus 2. So because we can add these directly and we can ignore the 1 due to associativity, we're going to get 2 to the k plus 2 minus 1 equals 2 to the k plus 2 minus 1, and hence we have proved it. Hope this was helpful. I'll be posting up the other properties in separate videos because this is taking too long.